Welcome to Calculus. Today we will investigate approximating area with Riemann sums. We'll take a look at one example. For this example, I have given an integral of a function from 0 to 10. It's given in integral notation, but then I'm also given some information about the function in a table. And what I want to do is use a left-hand Riemann sum to approximate the integral according to these values that are in the table. So what we'll do just to visualize what this function looks like, we'll do that graphing task first. So I'm going to start by graphing the function from the table. So I'm going to plot these points. We'll start with 0, 7, and 1, 5. And I can assume that this is a piecewise function. So as I plot these points, I'm going to connect them with linear segments. We'll graph 2, 6. Again, connect it with a linear segment there. Graph 3, 5. So up till now, we've had very regular intervals. Each one is an interval of 1 on my x-axis. That continues at 4, 6. But then with my next coordinate, the width of the interval changes. We jump from 4 to 9, and my value at 9 is 7. So I've got a much wider interval for this fourth interval there. And then my last point that I'm going to graph is the point 10, 5. So back to a width of 1. So that's my piecewise function. That's my f of x here in this integral notation. Now what we're trying to do is we want to approximate this integral, which again we can think of as the area under this f of x curve, so between it and the x-axis, using a left-hand Riemann sum. So let's draw our rectangles. So if it's saying left-hand, it means that the left-hand corner of the rectangle will need to achieve the function value. So where I'll start with my first rectangle, it's got a width of 1, but I want it to have a height of 7 so that its left vertex is there at 7. There's my first rectangle. My second rectangle has its left endpoint at 5. So we note that with these vertical rectangles, they have different approximations and really different errors. It's not an exact calculation of the volume using the Riemann sum. For my third rectangle, I've got the corner there at 6. And then, like we noticed earlier, for my fourth rectangle, this is the last one that's interval of width of 1. Because my next rectangle has a width of 6, but it's all the way to 9 in terms of its width. So its height is at 6 across there, again, because that segment begins at a height of 6 on the left. And then for my final rectangle, its left corner is going to be there at 7 and a width back of 1. So visually, that's the approximation that we're making. We're going to approximate the area under that purple curve by calculating the area of those 6 rectangles. So we'll write here that this is approximately equal to the integral from 0 to 10 of f of x dx. And the way we'll calculate this is by area. So length times width. For my first rectangle, it's going to be 7 times 1. So height times width plus my second rectangle has a height of 5. It's also a width of 1. My third rectangle has a height of 6 and a width of 1. And my fourth rectangle has the height of 5, width 1. My fifth rectangle is the one that's much wider than the others. It does have a height of 6, but its width is much bigger. It's got a width from 4 to 9, so that's a width of 5. And then our last sixth rectangle there, height of 7, back to a width of 1. So now to get this approximation complete, all I have to do is add up that series of areas. So this is going to be approximately 7 plus 5 plus 6 plus 5 plus 30 plus 7. And adding that up, looks like we can group stuff. The 7 and the 7 will make 14. And add 6 to that's going to give us 20. Plus 2 5s is 30, and plus 30 is 60. So our approximation of the area under the purple curve that's defined here in the table is going to be 60 square units. Thanks for joining for this investigation of approximating area with Riemann sums. See you soon.